page 182, they talk to us about the fundamental theorem of algebra. Now, we actually have already been using the fundamental theorem of algebra for a while. We've been referencing it and utilizing it because we already needed it. But basically in section 2.5, they tell us that whatever the degree of your polynomial is, that's how many factors you're going to have, and that's how many solutions you're going to have. So if you have something with a degree of 3, you're going to be able to factor that down so that it has 3 factors and 3 solutions. And so to prove that to us, they go through and they give us numerous examples here in the textbook of that. Like the first example, we've got f of x is equal to x minus 2. All right, well, that is its own factor. So there's one factor, and if I solved it, there's my one solution. All right, look at the next one. I have a quadratic. That's a degree of 2. And sure enough, if I factor it, I get 2 factors, and I get 2 solutions. And we can keep going from there. Please notice, though, that when you get something like an answer of plus or minus 2i, that's positive 2i and negative 2i. So that does count as 2 separate answers. I could write that as 2 separate factors, that type of thing. And so they go through and show you that with a degree of 4 solutions and 4 factors, a degree of 5. They even had to go through and do the P over Q and the synthetic division stuff to solve it. But they're still able to come up with 5 solutions and 5 factors. That doesn't mean they're all 5 going to be real. You'll notice several of these had imaginary solutions. Or they might have irrational solutions. Imaginary and irrational aren't going to be found by doing P over Q, but they are still solutions. All right. So then over on page 184, they talk to us about conjugate pairs. All right, look at this last piece right here for just a second. X squared plus 4 is equal to 0. That last piece of example number 3. All right, if I were to solve that, I would subtract the 4 over to the other side, and I'd take the square root of both sides. When you insert a square root, what do you always put in with it? Plus or minus. The only way that you can get an imaginary is by having the square root of a negative number, right? And anytime you're solving and you insert a square root, you're going to have inserted a plus or minus with it. So for that reason, imaginaries are going to come in pairs. And that's what they tell me on the top of 184, that if you have a polynomial that has a plus bi as the 0 of the function, then its conjugate a minus bi is also going to have to be a 0 of the function. Because there's no way on this problem that you could have gotten 0 plus 2i without getting 0 minus 2i. The only way that I could have an exception to that rule is if I had some type of a funky scenario. Like in the rule it says, let f of x be a polynomial that has real coefficients. That's a prerequisite. Because if I had something like this guy down here, these are not real coefficients, right? They're imaginary. So if I take out a common factor of I, I'm left with x plus I, and no, there's not a conjugate pair for that. I don't get x minus I. But the only reason for that is because I did not start with coefficients that were real. Anytime I start with real coefficients, then I'll come up with, if I get one conjugate, I will get a pair of them. It's like buy one, get one free. They always come together. All right? So we get to example number 4. And it says, find a 4th degree polynomial with real coefficients that has -1, -1, and 3i as 3 of its solutions. So first off, I automatically know what my 4th solution is, right? What is it? -3i, right, because those imaginaries come in pairs. So if I have plus 3i, I'm going to have minus 3i. Now we're right back to what we were doing in section 2.2, where they said, okay, if we give you the solutions, you work your way back to the original polynomial. We're going to give you the answer, you work your way back to the question. So remember the way that we did that was we took them from their solution form to their factor form. Now, remember to write something as a factor. A lot of you can just look at this and automatically see its factor form. Fantastic. But remember that if you're trying to write something in its factor form, it's just going to be equal to 0. So think about what would it take to make this equal 0? Well, I'd have to add that 1 to the other side. Okay, well then it's x plus 1 is equal to 0. So of course this guy is the same solution, so it's the same factor. what would the factor form for this one be? X minus 3i, right. Because if this is going to be equal to 0, I've got to subtract that 3i to the other side. So if I subtract the 3i to the other side, that'd be x minus 3i equals 0. What would this one be? X plus 3i, right. So now that I have each of them in their factor form, let's string all of those factors all together and just set them equal to 1, 0. So x plus 1, x plus 1, x minus 3i, x plus 3i. Now you might remember when we did this before, I think the actual example we had was like x plus 1, x minus 2, x minus 1, x plus 2. And we said we can start over here and just work our way straight across. If I take x plus 1 times x plus 1, I'm going to get the trinomial. I'm going to FOIL it out and get x squared plus 2x plus 1. And then I'm going to try and multiply that trinomial by this and get all kinds of nastiness. And then I'm going to try and take that thing and multiply it by this. We actually found out when we did this before, we found an easier way to do that. We found something to look for. What did we look for? Yeah, the conjugate pairs, or something like a difference of squares, right? Like when we put x plus 1 and x minus 1 together, it was so much faster and easier because it gave me a binomial instead of a trinomial. That's true here. When I multiply these two, it's going to be easier because I get a binomial. But more important than that, I'm going to get rid of some of those imaginaries. Whereas if I were trying to distribute a trinomial to this, I would end up with just all kinds of imaginary stuff everywhere. So absolutely, we want to go through and multiply these first two together, but rather than take that trinomial times the x minus 3i, we absolutely, anytime we see conjugate pairs or we see difference of squares, where you've got like x plus 1, x minus 1, or x plus 3i, x minus 3i, I always want to put those together first. All right, so if we FOIL these together, we were just doing this back in section 2.4. I could FOIL these together, first, outer, inner, last. We've seen that the outer and the inner always cancel each other out, so we set a shortcut for that. With these conjugate pairs is first term squared minus last term squared. You could do that. That I squared is -1, so -1 times -9 would give us +9, so we would have x squared plus 9. So that's going to be a whole lot easier to multiply that trinomial times that binomial than it would have been to multiply that trinomial times this binomial with the imaginaries and then times another binomial with imaginaries. All right, so if we go through and multiply, we could say x squared times x squared is x to the 4th. X squared times 9 is 9x squared. 2x times x squared is 2x squared. 2x times 9 is 18x. And then 1 times x squared is x squared. And 1 times 9 is 9. And then we just need to combine like terms and put our answer in descending power order. So we'll start with the highest power, x to the 4th. I didn't have any other something to the 4th terms to combine with it, so no like terms for that. X to the 3rd, I just had the 2x to the 3rd, nothing to combine with that. X squared, I had 9x squared and 1x squared, so I can combine those to be 10x squared. And then nothing to combine with the 18x and nothing to combine with the 9. Now this problem, just like when we did this before, in the back of the book it would say something like answers may vary or more than one answer is possible. The reason for that is you could then go through and multiply this whole thing by a +2 or multiply the whole thing by a -6 or whatever you want. You're still going to get those same solutions if you go through and multiply the whole thing by a coefficient where you distribute it all the way through. Kind of that idea of the number out in front that causes the vertical stretch or shrink. Just because you stretch it vertically or shrink it vertically, you're not changing it all horizontally. You're still going to hit the x-axis in the exact same spots. So those x-intercepts or solutions wouldn't change. All right, then example number 5, over on page 185, they give me a couple of bold print terms, irreducible over rationals and irreducible over reals. In order to really understand those two terms, I need to do a little bit of legwork first. I'm going to go through and I'm going to solve that quartic and get all of my solutions, and I'm going to write them in their solution form, and I'm also going to write them in their factor form. And what we mean by that is, remember, like right here, this was the solution form, this was the factor form. Okay? So if I have this quartic, this is x to the fourth, but it's a quartic that's in quadratic form, because if you square this, you get this, and this is a constant. So we've seen this numerous times, where we've said we could take x to the fourth and make that x squared times x squared, and then see what would multiply to be negative 20 and add to be negative 1. So that's where we're getting the negative 5 and the positive 4. We've also mentioned that if it's easier for you to see, that you could replace this with a y. So then that would be y squared minus y minus 20. And you could factor that to be y minus 5, y plus 4, and then just put the x squareds back in for the y's. That's fine too. Okay. Now, in the textbook, they go through and they factor this one down like a difference of squares. I don't know that I would have looked at 5 and saw a difference of squares. Since it's not a perfect square, I wouldn't tend to think of that as the square root of 5 squared. I probably would have been more likely to solve it this way, where I would say, okay, let me add my 5 to the other side, and then let me take the square root of both sides. And remember that when I take the square root, I insert that plus or minus. And just a little side note here, when I get positive and negative square root of 5, that's an irrational number, non-repeating, non-terminating. All right? Then my other one, I've got x squared plus 4. So if I came over here and solved that, subtract the 4, and again, take the square root, don't forget your plus or minus, and we'll get 2i, and of course those are imaginary. So those are my 4 solutions. Negative square root of 5, positive square root of 5, 2i, negative 2i. And I could go back and write them in their factor form like we were doing a second ago by just setting them equal to 0. So add this square root of 5 to the other side. Subtract this square root of 5 to the other side. Subtract this 2i to the other side. Add this 2i to the other side. So here's its factor form. Now when they say that this is irreducible over the rationals, they're saying to reduce this down further, if I want it to be irreducible over rationals, that means I can only use rational numbers in reducing it down further. Well, to reduce this one down further, to get down to its factor form, I need an irrational, right? Can't do that. And to reduce this one down further to its factor form, I need an imaginary. Can't do that. If all I'm allowed to use is rational numbers, then that can't be reduced any further. Then they talk about irreducible over reals. If all I can use is real numbers, then yeah, I could go ahead and break this one down. Square root of 5 and negative square root of 5 are real. They're not rational, but they're real. However, I still can't break this guy down, because to break him down further, I need imaginary numbers. So if all I'm allowed to use is real numbers, then I still can't break this down any further, because it would require imaginaries to do that. So that's that terminology there on 185. All right, last thing that we want to look at is similar to example 6. I actually pulled number 54 out of the exercises, but similar to what we did in example 6. It says, find all of the zeros of this quartic given that 2i is one of your solutions. Okay, if 2i is one of my solutions, what's another solution? Negative 2i, right. So I could put those in their factor form. This is their solution form, this is their factor form. And I could FOIL them back together, as we did. We've done that exact same problem earlier today, where we FOIL it back together again and we get x squared plus 4. So here's the deal. If I know that those two are solutions to this quartic, and I've put them together, combined them to be x squared plus 4, if this is one of the factors of that quartic, if I divide the quartic by one of its factors, that gives me the other factor, right? It's that same thing we've been saying all week long. If you're dividing 30 by 5, you get the other factor of 6. So I could do my polynomial long division. You don't need to write that down. For your polynomial long division, you could just say if I divide this into this, I get this, because we've done that repeatedly. The answer that I get is that other factor, and that other factor is a quadratic. I know how to solve a quadratic. Either factor or completing the square, quadratic formula, whatever you want, there are my other two solutions to that guy. So really putting together all of the ideas from 2.1 to 2.5 in that one problem to see what we can do with it. Okay? All right, so here is your homework for tonight on pages 187 to 188.